Hello and welcome to this Swift programming video. My name's David Thorne. In this video I'm going to try and teach you all about pointers and how to dereference pointers and also how to allocate some memory. With that said, let's just jump straight into it. And so the first thing we really need to do is understand variable addresses, okay? And when we say that, we're just going to comment this out. We're going to create an integer and we're just going to call it x first of all, and we're going to say it's 10. All right, and if we just keep it nice and simple, we're going to say x value equals, and then we'll just say ampersand d, do a bit of that there, and say x here. And when we run this, you'll see x value is equal to 10. That's all fantastic. We've seen all this stuff, but how do we now get the address of x? Well, let's just change this to say x's address is equal to now, and we'll just say p. And now we use this ampersand, right? This ampersand is saying, hey, now give me the actual address of x instead. And when we run this, you'll see that we get the memory location as well. And if you're a little bit skeptical about this, then let's just say ptr x2 and equals x, and run this code with a breakpoint as well. You can see down here that it's even telling us in the background that it is 0x16fd ff30c, and when we print this out, you're getting exactly the same thing. So even the debugger is telling you what the memory location was is correct. Okay, so let's just get rid of this now and continue. So now that we have this address, right, if we want to be able to dereference, so this is now x's, let's say the star value, all right, and we can say d once again. Now that we have this address, okay, we can now say, hey, give me the value that's at that address, because once we have an address, we don't really care about what the variable was, you know, because this, for us now, this we could now, if we run this again, we won't get the same address, okay? We're not going to get the same address. Oh, we did get the same address, but that's by chance that we've got the same address. Let's just assume that we did. You could essentially have the address written as hexadecimal and then go access that piece of memory. But because the memory address could be changed at any one time, it's not really very realistic to do. So, but because this ampersand x is basically synonymous to this address down here, we can say, hey, go into memory and now tell us what the value is at that one address. And we know that this is a integer pointer, right? So it means when we dereference, or when we say give me the dereference value at this pointer integer's address, that's the whole sentence here. You can't just say give me the value at this address. There's predominantly normally, you are normally telling it what type of pointer it is and what value, what type it's pointing to. So when we run this once again, you can see here that we get this, the dereference value, or the dereference address, sorry, it should be really, address value, let's just say is here, is then 10. Which is all really good. All right, so let's now create another variable of y, and let's equal that to 12. Okay. Now we can also create a ptr y as well, and we can say then the same thing as ptr y is then ampersand y, and just for the sake of printing it out as well, we'll print it out just to show you that we get y, and let's just put the address here as well, just to make it easier, and do ampersand y here too. When we run this, you'll see that we get the value of 12, and we get the address that we've got at this, which will be the same as ptr_y2. As you can see, it is. So now that we have this, if we want to, as I said, we don't have to worry about this one variable or this one variable here. As long as we've got that address, we can now assign another value. So if we want to change the value of x, we could change the value of x like this. But if we don't know the name of the variable, but we just got the memory address instead, we can then say ptrx, right? And we can use the star again, and we can say that we want it to be equal to 20. And when we run this piece of code here down the bottom, you'll notice, let's just move this over so that build succeed. You'll notice here x value is now equal to 20. So we've said, hey, Now set, because we're using the assignment operator, set the value at this one address, because we're dereferencing it using the star, to 20, all right? Now, however, if we turn around and said ptrx is equal to now ptry, so now we're saying set the memory location that's stored at ptrx to the value at ptry, right? And the value at ptry, because it's a pointer, is the address of y, right? But remember, when we say star ptry, we're saying give me the value at the address, right? At the address stored inside that one there. So now when we run this, you'll see that x stays the same as 10. And now when we copy and paste this once again, put a y there, and we do to do y here as well. I think we need to copy that, but to do y here, you now see 20 because we changed the pointer's address here to be that of ptry. So the biggest thing to take away from this is that a pointer is storing an address in memory, and you can go to that place in memory and then look inside that box and see the value there, okay? Or you can use the star with an address here. So use the star with an address and say, hey, give me that one value, and that's exactly what it's doing. Now, the ptry, that has its own address as well, but at the value of that one address is stored an address of y. Okay, so we can get the address of the pointer too. So let's do this, and let's just change this here. Now we, rather than saying the ampersand x, we'll do the ptrx here, and now we can just do the ampersand of this instead. So now we're getting the address, and if we do two addresses, so we do $p, and then we say ptrx, and we run these both, you'll see now that we get 308 and 2f8. So this here is the address of this, and the value of this one here goes to at the moment y, okay, because we changed it. So this is how the pointer addresses, dereference the addresses, work. So now there's something else that we want to talk about is, we've talked about dereferencing them. We can now look at the likes of arrays, okay? So let's come here and make a simple array, and we'll just call it items, and there's going to be 3 elements in this one array, and we're going to say 15, 20 and 25. Now if we want to create a pointer to this one array, what we do is we use the logic that you have to think about is that you're going to create a pointer to the first element in this one array, which will be then 15. So we say, let's just say ptr item, all right, and this is going to be an integer pointer, and here we're going to say ampersand items, and we're going to say we're going to go to the first element in there. So now when we print out item value, okay, here, let's spell it correctly, item value, and then d, do that there, and now we can say dereference ptr item as well, printf, and now you can see item value is 15. So what about if we want to then access the second item in this one array? Well, we can do this one of 2 ways, okay? We can, let's just do it both ways for the different things. So this is then item value 0, and this is then 1, and this is then 2. We are saying that we know that we have a pointer here, right? This is just dereferencing the first element, but we need to move forward a memory location. We know that we're working with an integer. Because we've got a pointer, we can wrap this in brackets here and just say +1, all right? And what we're saying is, from this pointer, move forward 1 memory location. And the one is this called a stride, from as far as I'm aware, is that 1 memory location is the size of an integer, all right? So it's going to move forward those amounts of bytes. And now what we're saying is, give me the value at that 1 pointer location, And when we run this again, you can see that on the second one we got value 20. This one here, the first index, so we got value 20, and the second index still got 15 because we haven't changed it yet. Now, to talk about this item here, we know we're accessing already an array because we're at the first item, and arrays are already pointers in themselves. Okay, so we don't need this dereferencing because we already are an array by doing this. So if we turn around and do 0 here, and you'll see that we still get 15, and we do 1 here, and we get 20, and we do 2 here, we then get 25. So we get something for free here. We don't have to use any dereferencing with arrays because they are already pointers, all right? And the C compiler already knows this is a pointer, and it knows what subscripting is to say, hey, move forward. This is doing, basically these are doing here, well, if I said 2 here, they're doing the same thing, right? This here is just a subscript of basically this, all right? And they're doing the same thing. So let's just change that back to 1. And you can see now that we get 15, 20, and 25. It's really important to understand how you can move through the locations in the addresses, all right? And the biggest thing to take away from this is that if you don't see a star, then we know that we don't have a pointer, just have a normal variable, okay? And if you have a star, then obviously we then have a pointer. We have an address, a pointer to another variable. Okay, so the next thing we want to talk about is actual memory allocation. And we're going to go over this very, very quickly. But if we want to actually, remember all of these X and Y, and also these pointers here, they've been added to the stack, right? They're part of the application. And so it means that they have their own specific memory addresses relative to where the application starts. But if we want to dynamically create memory, or we're going to hard code it into this, but we're just going to show you now how to create a variable instead. And when you're creating memory, remember you are creating a memory location, which means you're creating a pointer. So we're just going to create an integer pointer, and we're going to call it Z. Right? Really, we should just call it a pointer Z. And here we're going to say malloc, and this is going to allocate memory. Okay, it's a nice shorthand for allocate memory. Okay, and in here we're going to tell it the size of what we want to create, and we're going to create an integer, all right? And we only want one of them, so we don't have to say times 1 because it's already going to tell us the number of bytes to be created for an integer on this one system. So now we have this pointer Z. We can turn around and create actual Z. And here we just say pointer Z itself. So now we have Z. So we can come here and we can now say what Z's value is going to be. And we'll say Z here. And then we'll say pointer Z here. Now, before we run this, you have to remember that if you are going to allocate it yourself, you have to free it up yourself. These pieces of memory are all managed by the C compiler, by the operating system, and so on. But we, as a program, are managing this memory ourselves. So we have to make sure that we free it up after we've finished as well. We're just going to come to the end of the program, and we're just going to say free. Right, and this is going to free up any memory that was allocated for it. So we run this once again. You can see that we get Z is equal to 0, and that is the memory address. Completely different memory address now that we've got. But obviously Z doesn't have a value right now. So let's just give it a value of 100 instead. And we run this, and we now can see Z has a value of 100, and that is its memory location. Okay, now let's just show you a mistake that you could make. Remember, malloc is returning an address in memory. So if we turned around and said F, for example, and malloc, and size of, once again, it's going to be an integer, and we say F is equal to, let's say 120 here, and then we say, okay, we're going to free F, free F as well, right? This, you might think you're creating a piece of memory, but you're actually creating, well, just to show you instead. You see, this is going to crash here because when this malloc malloc returned a pointer, right? And here you're assigning it to not a pointer. You basically return it to an integer. So this is completely wrong. You're always creating a pointer when you call malloc, all right? So, and when you call free, you need to be freeing a pointer, all right? So it's saying, hey, free all of the memory at this one address. And so this is a mistake that you need to make sure that you understand. With that said, let's just clean this all up so it works again. With that said, this is a brief introduction to pointers and memory allocation. A brief, I want to say. There's a whole bunch of other things that you particularly need to understand, but I hope that this has been worthwhile watching. If you did, don't forget to like, subscribe and share, and don't forget to do all of the other social media things that could be done out there. If you've got any questions, feedback or concerns, then let's start a conversation in the comment section down below. Now, I am no master at the C programming language or C++, but I know enough to get by. But I create these videos in the event that I do any other videos of any other languages, like in Swift and so on, where we need to maybe access the C language. So please remember, my expertise is on Swift and other things. And if you want to listen to other people who are experts on C, please feel free to do so. But I try to give the information at a very, very basic level to teach people the basics. If you want an advanced expert level, there are definitely other channels out there. But I think I've managed to teach it well enough in this one video for you to have a good understanding of pointers, memory allocation, dereferencing, and a little bit of pointer arithmetic as well. With that said, thank you very much for watching. My name is David Thorne. See you in the next video. Ciao, ciao, and goodbye.